Hey everyone, today we're going to talk about the binomial distribution. It's going to be a brand new distribution that we have not talked about yet, and it has specific properties that make it binomial. So we're going to talk about what makes a setting a binomial setting, as well as how to calculate binomial probabilities. So the first thing you need to consider is the following. What is the difference between the following two situations? Let's say the probability that it is to rain is going to be 0.3. What's the probability that it will rain the first 2 days in February? So when you're thinking about the first 2 days, I want you to think about, we're talking about the probability of it raining and it raining. So rain and rain. If we know that it's the first 2 days of February, we're specifying that it's going to rain on the first day and it's going to rain on the second day. So rain and rain, we would just multiply. Rain times rain, and that's success times success. So we're going to let P represent the probability of success here. And in this case, we're defining success as rain. So it doesn't necessarily have to be a positive thing to be called success. So rain and rain just multiply. But now if you shift gears to number 2, it says, what is the probability that it will rain 2 out of the first 10 days in February? So here's where things change a little bit, because if there are 10 days, let's pretend like this is 10 plots, it could rain on the first 2 days, like we said before, or it could rain on the first day and then maybe not rain until the 10th day, or it could rain on this day and this day. We don't know. There's all these different combinations of rain that could be happening. So as soon as we say the word combination, we're incorporating actually a probability technique called combinations. And we want to know how many combinations are there of 2 days of rain out of 10 total days, 2 of which being rain and actually 8 of which being not rain. And that's where things get a lot more complicated. And that's where the binomial distribution comes in and the binomial probability formula comes in. So if we look down below, we have a new definition here, and it's the definition of a new distribution called the binomial. So you guys remember the normal setting was n, capital N, and then we would dictate it with the mean and the standard deviation mu and sigma. And that would kind of describe that it was a normal distribution with mean mu and standard deviation sigma. Similarly, here we have a capital B for binomial, and that's this one here. And then we have n comma p. The n comma p stand for important things that have to do with the distribution. So first of all, n is going to be the total number of trials, and that's really important. It's a finite number of trials, a countable number. So n is the finite number of trials, and I'll explain more about what that means shortly. And then the p is the probability of success. And success is whatever we're defining as success in the setting. So it could be that it's rain, so then the probability of it raining would be success. And we'll talk more about that last example in a second, but let me go down to the things that we need to know or memorize in order to determine if something has a binomial setting. So you guys can remember the word bin, B-I-N-S, and it's detailed here on the left-hand side. B-I-N-S is going to help you to remember the 4 things, the 4 qualifications that make a setting a binomial setting. So the B stands for bi. Bi means 2. So think about bicycle has 2 wheels, right? So bi in this case means each trial can only fall into one of 2 categories, success or failure, okay? So I want you to think back to above the do now, we said rain or not rain. Success is rain in that case, failure is not rain. So you're either raining or you're not. There's no in between. Similarly, we throw in a basket, it either gets in the hoop or it doesn't get in the hoop. There's no like it's stuck on the hoop, whatever. It's just in or not in, heads or not heads, rain or not rain. That's it. The I stands for independent. Each trial must be independent of the next. It looks like I switched these two. The I stands for independent. Each trial must be independent of the next. And that can either be assumed or it will be stated in the question. So for example, with subsequent coin flips, for example, we would assume that each coin flip does not affect the next. The N stands for there is a finite number of trials, and that actually is the most important one. So I'm gonna go over here and I'm gonna star the N. I know they should have been switched, but the N is a finite number of trials. This is the most important thing here that will help you to know that it is indeed binomial. So if you look back at the example I gave you on Do Now number 2, it said it will rain 2 out of the first 10 days of February. So the N is 10 total days. So that is a finite number. So that is good because it's falling into that qualification. And the last S means success, and is the probability of success must be the same for each trial. So think S, success, same, SS. Success has to be the same. So in the case of rain, for example, that would be the probability of rain would be the same for every day in February. So that's not really true in real life. You guys know that it probably changes depending on any given day based on the fronts coming in and out or whatever's going on with the weather. But in this case, we're assuming that the probability of success, which is rain, is going to be the same no matter what. So does this category qualify for the binomial setting? Does each day fall into one of two categories, rain or not rain? Yes. Success or failure. I'm going to call not rain 1 minus P. I'm going to call that failure, and that's going to be called Q, and that would be not rain. And the complement of rain is not rain. So 1 minus 0.3 is 0.7. Those have to add up to one whole, right? So we have that. We're going to assume that each day in February is independent of the next, which again is not really true in real life because subsequent days of weather may affect each other. The N was a total of 10, that was finite, and the probability of success we're going to assume is 30% per day. So if all these 4 conditions are met, it is considered a binomial setting, and then you can proceed with binomial formulas. And I'm going to show you those in a second. Let's look at another example. Example 1. So now let's just say that the genes children receive from their parents are independent of each other. So I'm going to circle that. That's already the I for bins, so that's good news. Okay. Each child of a particular set has a probability of getting type O of 0.25. Okay, so they're already saying that we're going to let P be success. We're going to let the probability of getting type O blood represent success, and that's going to be 0.25. So if you look at the P for Vince, does each child fall into one of two categories, success or failure? You either can get type O or you could not get type O. So we're going to let failure be not type O. So the complement of success is failure. So we have 0.25 for success and 0.75 for failure. So that is met. They stated that each child is independent of the next. That's also met. Now the N stands for, is there a finite number of trials? So it says these parents have 5 total children. Okay, so we're going to let N be 5. Each child is representing a trial. And because this is a finite number, that N is met. And then the last one is the probability of success the same for each child? So we're going to assume that the probability of getting type O blood is the same for each child, and that's 0.25. And if these 4 conditions are met, it is indeed binomial. So we're going to say, yes, this is indeed binomial. And thus, I'm going to be able to apply the binomial setting. Now, if you look at the next example, I want you to read it over and then tell me if you think that it is binomial or not. Okay, so I am hoping you said no for this one. And I'm hoping you said no for a specific reason. Is there, does each trial fall into one of 2 categories, success or failure? I'm hoping you said yes. We're looking at ACEs. So the probability of an ACE is considered success. The probability of getting an ACE in Clear Deck is 4 out of 52. So the probability of failure would be the probability of not getting an ACE, and that's just going to be 1 minus 4 out of 52. Okay, so that one is met. Is each turnover independent of the next? I'm hoping that you said no, because it says that we're turning over 10 total cards, which is the sample size n. So that one is met. But if you turn over a card, you should know that there's one less card in the deck. And if there's one less card in the deck, then the probability of getting an ace is going to be different from card to card. So I want you to say no, it is not independent because each card is not independent of the next, because it sounds like we're taking 10 cards out of the deck without replacement. And we're not putting them back. So how could we alter this? I'm hoping that you would say we would have to draw a card and replace it. And shuffle well basically every time. So that way we can really see that it's an ace or not, and then you put it back, shuffle it, do it again, and do it 10 total times. So even though there were 10 total finite number of trials here, it was not independent in part A, so we would have to alter it in order to apply the binomial setting. All right, so now you're probably wondering, how can I actually evaluate this stuff? And what you're going to see is there is a formula on the formula sheet, and this is an excerpt from it. I'm going to show you what it looks like on the formula sheet as well. Let's see if I have it here. Looks like I don't have it here. There is on the formula sheet, it is right underneath the discrete random variable. I'll see if I could pull it up in a second, but here is the formula. All right, so here is the formula sheet. Right under where it says discrete random variable, you see right here in this box, it says if X has a binomial distribution with parameters n and p, then, and it has this formula here. All right, so I'm going to show you what this means right now. Instead of k here, it looks like they're using x, but it means the same thing. Okay, so it says when x equals x or k, I'll just use k for the sake of this worksheet. The n is the total number of trials. Remember, it's finite. The k, or the lowercase x in the other one here, is going to be the desired number of successes. The p is the probability of success, whatever you guys are defining success as. And the 1 minus p is going to be the probability of failure, which is just not success. And sometimes we call that the letter Q. Okay, so I'm going to show you how this applies to the question that I skipped before. So if you guys scroll down this question, revisit example 1, it says geneticists say that the genes they receive from their parents is independent from one child to the next. Same question. Each child has a probability P of getting type O blood of 0.25. So that's called P, lowercase p. So the complement of P is 1 minus P, we said, is 0.75. And that's not type O. Okay. So now we already have success and failure. It says we have a total of 5 children, that's n. And it says find the probability, which we're going to call capital P, that exactly 1 out of the 5 children has type O blood. So the desired number of successes that we want is 1. Okay, so we're going to write P x equals 1, and that means the desired number of success. And now if you look at your reference sheet, it says n over k. So you're probably wondering, what is this thing? Okay, this thing is called a combination. So I'm going to bring it to the side here, and I'm going to explain. If it's n over k or n over x, it doesn't matter. This actually means n c k, where n is the total number of trials and c is the combination and k is the desired number of successes. So in the case of the type O negative situation, there were 5 total kids, and we said we wanted to have one of them have type O blood. So it could be either written as 5 over 1 like that, or it could be written as 5C1. What does this mean? This means that how many ways can we arrange having one of those kids having type O blood? So think back to the February rain situation, right? In this case, we have 5 children. How many arrangements can we make of one of those 5 kids having type O? It could be here type O and then not. Or it could be the second child could have type O and then not, etc. Okay. So how many total combinations of that are there? There's probably 5, okay? So how can you find that out? You actually can plug that 5C1 into your calculator. I'm going to show you how. So in your calculator, you guys are going to press 5, the number 5. Then you're going to press math. And then you're going to go over to where it says prob, and you're going to go down to the one that says NCR. So again, I press 5 first, then I press math, then I press prob, and then I press 3, which is NCR. And then I'm going to put in whatever I want. So if I want one kid to have type O, I'm going to put 5C1. And when I hit enter, I'm going to get 5. This means, this means that there are 5 combinations of getting one of those 5 kids having type O blood. So going over to this, I'm going to just show you again how to plug into the formula, okay? So it says N over K. So that was 5 over 1, okay? Then it says P to the K. I'm up to this part here, guys. I'm going to color code it in green, okay? P to the K. So the probability of success to whatever desired number of success we wanted. So the probability of success was type O blood. So in this case, it was 0.25. So P to the K, or X, I should say. So 0.25, and we want one of those. Boom. And then what is the probability of failure? So if you look back again at the formula, it says 1 minus P to the N minus X, or N minus K. So 1 minus K is failure. 1 minus P is failure, sorry. It's 0.75. So this is going to be 0.75. And how many do I want of those? 5 minus 1 is 4. All right, so this is how you would set up the formula. Okay, it's a combination. So how many combinations can we arrange of 5 kids, one of whom having type O blood? There's 5 of them. Then the probability of that happening is 0.25 to the 1. And then failure, 4 of them basically are going to not have type O. So one of them is going to have type O, and 4 of them are not going to have type O. So then you could either put this in the calculator like exactly how you see it, and I'm going to show you how in a second, or there is another calculator function for that, okay? So here we go. First, we're going to put in the whole thing exactly like this, and I'm going to show you what we get. So you're going to press, same thing, 5, math, go over to prob, go down to the 3 for combination, 1. So this means how many combinations, again, are we going to have? Parentheses. Probability of success, 0.25 to the 1, and then parentheses, 0.75, and how many do we want of those? We want 4. So when you do this out, you're going to get your probability, and I got 0.3955. So write that down. That means the chance or the probability of having one of your 5 kids having type O blood is about 39.55%. So if we took many, I'm not going to write this down. I know it says interpret. If we took many kids and many families like this, there would be a 39.55% chance that one of the kids would have type O blood. Now I'm going to show you how to use the calculator function. So go over to this box here, scroll to it. I'm going to show you what to press. So do you guys remember when we did second vars and we would do normal CDF? We're going to go back to second vars, but this time we're going to use a different distribution. It's going to be binomial. So keep scrolling until you find letter A. Letter A is binomial PDF. We are going to choose that one. So let's write that down. We're going to do second vars, and we're going to scroll until we get to, for me, it's letter A, binomial PDF. PDF stands for probability distribution function. Okay, choose it. And then you're going to put in the total number of trials, which is the N. See, the trials is the N. So like 5 kids, for example. The probability of success, that's going to be the P, which was, I think, 0.25 from what I remember. And then the X value is going to be, or the K value is going to be the desired number of successes. So the desired number of kids, in this case, who you want to have type O blood was 1. Okay, I know I'm spelling success wrong every time, but just go with it. So we're going to press trials 5. We're going to press probability of success 0.25, and we're going to press X value 1. Uh-oh. When you hit enter, you're going to get your answer, and guess what? It's going to be the exact same answer as above. So the binomial PDF function will do the binomial formula for you, and you do not have to do it yourself, which is beautiful. But you're probably asking yourself, how am I going to get full credit on the AP if I use binomial PDF? And the answer is, you're going to do the exact same thing that you did with normal CDF. You have to tell the grader what kind of distribution it is, aka binom. So you would write binom or big letter B, and then you would have to write N, P, X. And then you can write your notation and go right to the answer. So in this case, it was binomial because we went over the bins for this question. The N was 5 total kids. The P was the probability of success, which was type O blood, 0.25. And the X was the desired number of kids who we wanted type O, which was 1. Then you would write P, X equals 1. And then you would just write your answer from the calc, 0.3955, and you would write from calc. Isn't that amazing? It is, but you have to make sure you write all the parameters down. Otherwise, you're not getting full credit. Now, if you look down below, we have a little blurb that tells you exactly what I just went over. It says state the distribution and the values that are important, the N and the P. Mine got a little cut off, but you guys should have it on your paper. Then perform the calculations, either using the probability formula or using the calculator. So I want you guys to try these. The next two, when you see them, I want you to at least first underline the key information and identify the N, P, and X. N, P, X, N, P, X. And I'm telling you that these are both binomials, so you don't have to check the parameters for it. So just circle the key information and tell me what's N, what's P, what's X. What's N, what's P, what's X, and then find the probabilities, and we will check them now. So did you guys write N equals 15 for the first one, 15 total trials, aka 15 total traffic fatalities. The P is the probability of success, which is being intoxicated, and the X is 12. Now let's see if you can plug them into the formula. Go. So here is the plug-in of the formula. I put it there for you, and now let's see if you can find the answer in the calculator. All right, so as you can see, I got 0.17004 for the answer, so hopefully you did as well. Now go on to number 2 and do the same thing. State N, P, X, and try to set up the formula and solve. All right, so for this one, we had a total of 3 children. So that's N, that's a finite number. And we wanted to know that probably exactly 2 out of 3 will have the disease X. So the desired number of successes is 2 out of 3. So that's the X value or K value. And the probability of success is 1 out of 4. So I'm going to circle that. That's P, the probability of success. So I set it up here and I have 3C2 or 3 combination 2. Please don't put a fraction bar here. This is technically not a fraction, 3 over 2. It's just 3 like floating over a 2. And that's implied to be 3C2. 1/4 to the 2, 3/4 to the 1, okay? And I got 0.1406, so let's see if you got it right. I do want to mention, like, where there's a misconception is that kids sometimes think that this is going to be 1 for the X value because they see 1 out of 4. So they think that means that you're getting 1 kid success out of 4. And that's not true because they're saying the probability of getting gene X is 1 out of 4. So the number of kids who have disease X is actually independent of the probability of success. Like the number of kids we have and the desired number of success, it's actually independent of that 1 out of 4. So like in this case, we have 3 kids, and 2 of which we want to have disease X. Those 2 and the 3 are independent of the 1/4, which is the probability of success. So that's a little confusing, I know. Okay, so I'm going to leave you with the following. I'm just going to talk to you a little bit about if it's more than just a one trial situation. So for example, if it says at least or at most, that's when your life gets more complicated. So I want to star these phrases here and say, as soon as you see the probability of at least or at most 2 kids having type O blood, that's when your life gets more interesting. So quick look, this is the same question. So just on the side, I'm going to still write N equals 5 children. P equals the probability of type O is 0.25, probability of success, P. And this time it says, what is the probability at most 2 kids have type O? So at most, hopefully you know, means 2 or less, aka less than or equal to 2. So this could mean that it could be 2 kids have type O blood, or 1 kid could have type O blood, or no kids could have type O blood. And I'm hoping you remember that or means add in probability. So what we're going to do now is we're going to find the probability of exactly 2 kids having type O blood and 1 kid and 0 kids, I should say or, and we're going to add, okay? So you may be like, well, that seems like that's a lot of work. Well, technically we already did it for the 2, I think, on the previous example. But you would have to, if you did this by hand, set up the formula for 2, 1, and 0 and add them up. So you would have to do the same pattern. You would do it for 2. So you would do 5C2, probability of success, to the 2, probability of failure, which is 0.75, to the 5 minus 2, which is 3. Then you would do plus. Now you do it for 1. 5C1, probability of success, to the 1, probability of failure, to the 5 minus 1, which is 4. Then you would do it for 0. 5C0, probability of success, to the 0, probability of failure, which is 0.75, to the 5 minus 0, which is 5. This seems really annoying. And basically, you would do binomial PDF, binomial PDF, binomial PDF, and you would add them all up. And it turns out there's a quicker way to do that, and that is called binomial CDF. So instead of doing this by hand and adding it up 3 times, you can use the function binomial CDF. So I'm going to show you that now. You would press second bars, and instead of going to letter A for binomial PDF, you're going to go to letter C, which is binomial CDF, and it's going to look exactly the same. You're going to still put in the number of trials, which is 5. You're going to still put in the probability of success, which is 0.25, and you're going to still put in the X value, and you got to make sure that you put whatever is less than or equal to the number that you want. So you're going to put in 2. So in this case, this means 2 or less. And C stands for cumulative, meaning accumulating. So this is really going to give you, it would be binomial PDF for 0, 1, and 2, and you would add them up. And that is the total answer. So we get 0.896-ish. And I want to show you that if I had done binomial PDF for the same thing, I'll show you it because I think it's worthwhile to show you. If we had binomial PDF, sorry, for 0, 1, and 2, and we had added it all up, we would get the same answer. So let me show you. I'm going to put in 5, I'm going to put in 0.25, and I'm going to put in 0. This is the probably exactly 0 kids would have type O blood. And then you would hit enter, and then you would do it for 1. So it would go here, and then you would type over the 0 and just put 1, hit enter, and then you would go here. This is again binomial PDF 3 times. And you would type over it and you would put 2, not 3, 2. And then what you would do is you would add those 3 up. So you would add up the 0, 1, and 2. 0 plus 1 plus 2. And you're going to get the same answer that we got for binomial CDF, which is 0.896, you see. So binomial CDF is nice because it gives you accumulating 0, 1, and 2, and it will add them up. So that is only for less than or equal to. And we are going to go over in class how to do the other ones because this video is getting too long. So I just want to mention, let's write this down. Second bars, B, binomial CDF stands for cumulative distribution function. It's going to give you the area less than or equal to the number, okay? So remember, it's the one at or below, aka at most. So if I put a 2 in here, it's going to be 2 or less to the left, okay? And we'll talk about going the other way tomorrow in class. So binomial PDF is for a single probability distribution. The word exactly is applicable. And binomial CDF is for accumulating more than one.